This is the first meetup organized by Singularity Data in Singapore. So the topic is about, the big topic is about the modern data stacks. So basically, we would try to invite a lot of external speakers together with, engineers at the Singularity Data to talk about anything about, technologies falling in the category of modern data stacks. So, if we manage to do so, then you probably would see more and more diversified speakers at this meetup. But if we fail to do so, then probably you will see me again and again. Okay, so this meetup, so I will talk about like the past, present, and the future of streaming processing. I admit that this title is a little bit broad. It's a little bit clickbaiting. But basically, I would cover like, really basic issues that people have solved and that people try to solve in the past, at the present, and in the future. Right. Okay. So basically, the outline will be we talk about the evolution of stream processing system. And we discuss about some of the key design choices made by these systems. And we would also show some use cases, like how people use stream processing system to deliver their real-time insights. And finally, we would talk about some future direction and challenges. Let's say when we want to turn stream processing system into a product. Okay. So the first question is that why do we need stream processing? The key characteristic would be stream processing can deliver insights with very low latency. Right. So for some applications, they don't really require low latency. For example, if we want to generate a financial report every day, right? So for some people to review, then probably for this kind of application, we don't need to use stream processing. Right, because we do not really care about the latency. But for some other applications that we need real-time insights and we can do some follow-up actions about these insights, then we probably need stream processing because we need to make some action right at that time. Right. So, for example, a simple example is that, for example, we are building an e-commerce website, right, and some users made a lot of clicks about different products. Then we want to really like record these clicks and try to guess what kind of advertisement or what kind of a recommendation we should make to the users in the user's next click, right? So we want to capture that part of value, let's say. And another example would be like you are making some risk detection or fraud detection application. Right. So, for example, you're checking users' transactions. Right. So, if they make some really weird transactions, you would think they are doing probably money laundering or their accounts is being hacked by other people. So, they are now really doing the transaction by themselves. So, you want to stop this kind of action right at that time. Right. So, if we have this kind of a demands, then we have to do stream processing and make these real-time actions possible. Right. And I think in recent years, there are more and more, let's say, decision is made by algorithms, by bots, and by machine learning models. Right. So for these cases, I think it is extremely critical because only like algorithms, models, and bots can capture the extra value that we deliver with low latency. So the question is that how should we do stream processing, right? So before stream processing, what we have is batch processing, right? Batch processing is basically designed for, high throughput instead of low latency, like in general. So we can kind of start with batch processing first and make a comparison with stream processing and see what kind of extra complexity stream processing is dealing with. At the very beginning, I think people do not really understand how they process very large volume of data in a distributed fashion, right? So until Google published their papers about MapReduce, people start to realize that how they can process a really large amount of data in a fault-tolerant way, right? So because MapReduce is already validated at Google scale, so people are confident that this is the right technology. MapReduce, as shown in this simple, basically you have some input data at some distributed file system, or let's say on disk, right? And then you have a lot of partition of these data, and each partition will be handled by a map task, right? Map task maybe do some transformation, and then each map task output the results to its disk, maybe local disk, maybe to a distributed file system. And for the reduce phase, it reads the intermediate results, which is output by the map task into the memory, and then do some other processing, typically which is join or aggregation, right? After this kind of processing, also in distributed way, it writes the output to some disk storage system, let's say. So this kind of architecture is designed for really large-scale distributed processing, and we want to handle very high throughput of data. The good thing about this MapReduce thing is that, first of all, it offers a very simple but expressive interface, right? So map and reduce are two primitives from functional programming languages. So they are also kind of already validated by long-term usage, right? So basically, you just need to write the logic in the map function and also the reduce function, and then your job is good to go. And they are very expressive in the sense that, I mean, all the SQL queries can, I think, can all be expressed in these two functions. Another advantage is that all of these map tasks and the reduce tasks are stateless, right? So if we consider like a map task is basically we're defining a function about input and some state. So this state here may be some prior belief, or maybe some state which is computed from the previous round of a MapReduce, right? So after the processing, after the map task, we have the new output and the new state, right? The good thing about this is that we don't really change the old state. The old state is immutable, right? So this is really easy for us to implement fault tolerance, right? Because if, let's say, one map task fail or one reduce task fail, we just rerun the task again because the input and the state are all there, right? And we can also implement some straggler mitigation strategy when we have some data skew problem, right? So suppose maybe some machine is not running quick enough, so we just spawn a new task for the same partition of the data and the partition of the state, and we run it concurrently, and whichever one runs finished first, then we just take the output of the first one, right? I mean, these kind of techniques is kind of a classic in the sense that, like nowadays when people talk about serverless architecture, these kind of techniques are still being used in some kind of a research paper. But the downside of this MapReduce architecture is that every input, every intermediate result, every output have to be written into the disk and then be read from the disk again for the next round of processing, right? So we have very huge latency here because these disk read and writes. So I think at the time, people also try to implement some iterative tasks like graph processing, like you compute the page ranks of some graph by using MapReduce, which is also very inefficient because of this kind of disk read and writes. So this makes low latency processing, basically stream processing, even impossible, right? So the next generation of this Apache MapReduce is called Apache Spark, right? Apache Spark is invented by a lab at the UC Berkeley, right? So the core idea we can see from these the difference of these two figures is that for Apache Spark, it writes the intermediate results to the distributed memory. Sorry. Any problem?
City House.
Okay. Yeah, we hold the event at the City House. Okay. So Apache Spark's advantage is that it keeps, like the data set or the state in memory as much as possible, right? So we don't need to do all kinds of disk read and writes, and the performance is better. And another, let's say, huge thing of Apache Spark is that it can do parallel recovery, right? For example, if let's say one partition of the state is lost, and then we can just spawn multiple tasks, right, to try to recompute the state from its, previous computation, right? So we can kind of speed up this process of recovery. And another advantage is that Spark divides, tasks, let's say jobs, into a huge number of tasks, right? So when you have a lot of finer granular tasks in finer granularity, then you can do better load balancing, right? So you can just assign them to all kinds of idle compute nodes. So by keeping the state in the memory, right? So this unlocks the possibility of stream processing because we can keep latency low. So the way Spark do stream processing is by reusing its batch processing architecture. So the name is called micro batch processing in the sense that it will accumulate some amount of data at the beginning, and then it just do normal batch processing for that macro batch of the data and then the output, right? So the advantage is that it just simply inherits all the advantage of batch processing, and it just reuses its code. So this is really a very neat way to do stream processing on a batch processing architecture, right? And because of this kind of an easy fault tolerance, we just get the exactly once processing semantics for the stream processing jobs, right? Because you would keep some, let's say, state in memory. You still need to checkpoint from time to time, right? Otherwise, if you lose the state in the memory, then you have to really recompute from the very beginning, which is normally impossible, right? Okay, so we will come back to this exactly once processing semantics in slides later. But the problem with Spark streaming is that it can only achieve near real time in the sense that it can achieve second level latency, but it cannot really achieve like true real time, like a millisecond latency, right? So one of the problems is that, because it divides the job into a lot of tasks, it needs to do task scheduling, and the task scheduling has some overhead, and this kind of overhead is incurred for each macro batch processing, right? And you also have a centralized coordinator. So when you try to do the task scheduling by this centralized coordinator, we naturally just meet the bottleneck when we try to reduce the latency, right? So there are also some attempts by the Sim lab, which implement Spark, try to solve these two issues. And these are like two papers. Wants to do like some distributed scheduling, or let's say group scheduling. So try to reduce the overhead of the task scheduling, so to keep latency low, right? Okay. So another problem with Spark streaming is that at the beginning of its, let's say when it's invented, it does not really have the support for event time semantics. Right? So the event times, the time semantics we are all familiar with is processing time, right? So processing time is the time when an input event gets processed. So for example, if let's say the Spark streaming accumulates the data for sometimes for this micro batch, and when this micro batch gets processed, this wall clock time is the processing time, right? But what we really need here is event time. Event time is the time when an input event is generated, right? So let me give you an example. For example, let's say we want to answer the question that how many times a particular advertisement has been clicked in a tumbling window of 1 minute, right? So the tumbling window is like the simplest window in the sense that each minute is a window. So all the tumbling windows along the time dimension are mutually exclusive, but they are collectively exhaustive, to occupy the whole timeline. Right? So for example, let's say a user make a click at A12, right? So when the event actually gets processed is at A13. Right? So if we want to answer this question, what we really want to say is, what we really want to count this event in is in the window starting from A12, right? So if we are using the wrong, using the processing time to do this query, then we probably would derive the wrong insights, right? So 1 minute here may sounds not too much, but we can always make the case a lot worse, right? So for example, the event is generated at A12, but actually it only gets delivered to the system at, let's say, 9:12, right? So there's 1 hour lag, which would make our analytics basically produce wrong results. So another natural question is that if we are using like processing time, right? So it's very natural for us to define the start time of the window and the end time of the window, right? So it would be A12 to A13. That's the one tumbling window, right? But if we are using like event time semantics, then the problem is that when should we close the window, let's say starting from A12, because we encounter an event which is generated at A12. So in ideal situation, like the left figure, right? So we always have the events coming into the system in order. So basically, if an event is generated earlier in processing time, then it will also deliver it to the system. It's generated earlier in event time, then it will also deliver to the system earlier in processing time, right? But this is not always the case because we can get the events from all types of sources, right? So if we have 1 million users, we probably get the events from all these 1 million users out of order. So the real situation is more like, so the real situation is more like the right-hand side picture, right? So the events can be delivered out of order. So the streaming people invented a concept called watermark to indicate that there will be no late events older than a certain time, right? So for example, we say a watermark of A13, it will indicate that there will be no input whose event time is older than A13, right? So this is really some artificial concept. So for example, if let's say we have, in reality, we have more events come into the system which have whose event time is earlier than A13, we would simply just discard them, right? So we just kind of make an artificial close of that window by using watermark semantics, right? So watermark is used to represent the temporal completeness of an out-of-order data stream, right? So some example strategy would be, these kind of strategies is totally user-defined. You should kind of design them according to your application or your knowledge about the data stream you receive for your application. Right? So a simple one would be monotonously increasing, right? So basically, we expect that all of the events will be delivered in order. So whenever we encounter an event who has a newer event time, then we can just conclude that all the events older than this event time will now come to the system again, right? And we can also define it as some kind of a bounded lateness by setting a fixed amount of lateness. Okay. So the question is that why do we need to close the window at the very first place, right? So the reason we close the window is that we want to really clean the state, right? So if, let's say, the window is keep opening, right? So we want to keep counting the number of clicks happening in this tumbling window. Then we just have to allocate some storage space, no matter in memory or in disk, for that particular counters, right? And the second one is that we want to output a finalized result, right? So if, let's say, we do not have this watermark, then when should we really do the computation, like output this count, right? If, let's say, we output the count and there are new events coming to the system, then we have to kind of count +1, count +2, and then we have to emit a lot of changes to the output, right? So we cannot really deliver a finalized result. But I mean, this kind of a strategy has no kind of a fundamental. It's not fundamentally wrong, right? It's really about whether your system or, let's say, your downstream application can deal with this kind of changes or not. Okay. So since the Spark streaming cannot really deliver true real time, there are also two other stream processes systems gets invented. One is called Apache Storm. The other one is called Apache Flink, right? So the difference in the architecture is that they do not process the events in micro batch. They just process each event, one event at a time, right? And they don't have immutable state. They would just change the state in place. Obviously, changing state in place would make things a lot complicated. So we can make a comparison between the micro batch processing architecture and this long running, or let's say one record at a time architecture. So on the left-hand side, we have already seen this before, and on the right-hand side, we redefined this function, right? So we can consider that for each event, we are event as the input, and for the state, we are really just mutate that state in place, right? We take a reference to the state and we mutate it instead of keeping the old state immutable and produce a new state. So so then the problem is that how can we recover from failure, right? So because in the batch processing, recover from failure is really simple. We just rerun the task again, the same task again. Okay. So loosely speaking, what we mean by correct is like for any internal state managed by the system, right? We don't want to let people tell whether the job has ever failed before. Right? So So the implication is that for this function, we want it to be evaluated once and only once for each input, right? So this state, the side effect of each event on this state is only, reflected once and only once. Right. Okay. So, right. So one kind of a semantics is called at most once, right? So it's not the credits we are looking for. We just try to understand what we need to do to make sure that we get these kind of credits. So one kind of a semantics is called at most once. This semantics is really trivial, right? Because you just make sure that you will never take in the same event more than once, right? For example, if let's say your upstream is a Kafka, and you try to consume events from the Kafka, then whenever you take some events from Kafka, you just commit to that Kafka first, and then you try to process your event, right? So if, let's say, the job failed and you want to kind of replay from the Kafka, you will get a new event instead of the old event you get still in processing, right? So another kind of a processing semantics is called at least once, right? So basically, each event has to be processed at least once. This is the semantics implemented by Apache Storm. So to make that guarantee, we need to track whether every input has been fully processed or not. So the tricky thing is about this, whether input is fully processed. The problem is that when we have a streaming job, when we have a lot of operators in this job, one input may be transformed into multiple output and for the next operator to process, right? So for these multiple output, we would always consider that they belong to the same input, right? And these outputs will be transformed into more outputs by the next operator, right? So what we really want to make sure is that like all the descendants of the input event has been fully processed. At least we want to tell whether it happens or not, right? So here we have to make a recursive definition is that all the children's message of an input need to be fully processed. So the way Apache Storm do it is that it tries to attach a unique ID to each input, right? And all of its children's message will also be attacked with the same unique ID, right? And then we maintain a counter for each unique ID. So for example, let's say we have an input coming to the system, we have unique ID 1, and we let one operator process it, and it produces like multiple children messages, right? So for example, 10 children messages. So what we do is that we try to add 10 to this counter, and we also minus 1 because we already processed the the root message, right? So if let's say all the message gets processed, then the effect is that we would just see this counter going to 0, right? So when this counter goes to 0, we can be sure that this input has been fully processed. So when the failure happens, it means that the counter will now decrease to 0. So we set a timeout on this counter. Like for example, let's say the counter does not go to 0 for like 5 minutes, then we just consider that this input has to be replayed, have to be reprocessed, right? So this is how Apache Storm makes this at least once processing semantics guarantee. And finally, we have what we really want is exactly once, right? So this is done by Apache Flink. I think one naive solution is like if we want to motivate the ultimate solution, one naive solution is try to do first stop the world, right? So it's like we just ask all the compute nodes stop, and then we take a snapshot of all the internal states capping the job, right? But the question is that how can we really be sure that there is no message flowing between machines? Because these machines is also kind of considered as part of the state maintained by this job, right? So we cannot like just discard them in the snapshot we take, because when we recover from that snapshot, we just lose this message, and we break the semantics, right? The way we can think about this is that we can let each upstream send a very special message after all the normal streaming messages have been delivered to the downstream, right? So if, let's say, the downstream received this special message from upstream, then we can be sure that, upstream has already stopped. And now, at least, let's say, for the upstream, we can take the snapshot of it. Then we can do this thing recursively, like from upstream to downstream, and then downstream to further downstream. And finally, when every node stops, we just take the full snapshot for all of the nodes. Then the question is that, do we really want to do this stop the world thing? Like, is it really necessary, right? So the Flink people will figure out that it's not really necessary to really stop processing, right? So as we can see from the this figure, right? So the special message we are talking about is denoted in yellow, right? So the yellow square thing, right? So this is what we ingest into the source and the most upstream, right? So the upstream would forward this special message to the downstream, and now we are looking at one specific operator, let's say, right? So it's taking 3 special message from 3 upstream, right? And in figure A, we can see that one special message has already arrived at its operator, so we can conclude that, in this snapshot, all of the things from this middle upstream has already delivered to this operator, right? So what we need to do is that we wait for the other 2 special messages arrive at this operator, right? Because all the messages before this special messages are considered within the same snapshot, right? So we don't want to misalign them. So we are basically taking snapshots of 2 different time points. So we can see that after 3 messages come to the operator, we call it alignment. So after we align them, so we can take the snapshot of this message and edit this operator. And at the same time, we can see that the upstream does not really stop processing its new income, let's say input, right? So so in this sense, we just only need to kind of forward this kind of special message, and when they align, we take a snapshot, and all the upstream and the downstream is not affected by this stop the world thing. They can keep just processing as normal. So this is the algorithm called asynchronously various snapshotting, ABS, which is a variant of Chandy-Lamport algorithm to take a consistent snapshot. So after we take the snapshot and when the system crashes, we can just reset the state to the last checkpoint, right? And then we just replace the input messages. Okay. So what we have talked about is called processing semantics. So what processing semantics can guarantee is that for any internal state, we cannot really tell whether the job has ever failed before, right? But since the stream processing job can also output some events to downstream application, and these outputs would be considered some external side effects, right? So for these side effects, it is not really managed by the stream system. It's managed by some downstream, like another totally different system, right? So what ABS can guarantee is that the exactly one's processing within the system instead of processing across to another system. Right? So the thing is that even we have ABS, when we fail, we still need to kind of replay something we have already processed before. So these processing, replay processing can kind of produce the same output twice to some downstream system. And in that sense, we cannot really kind of do exactly once delivery semantics. So we can consider these three cases again, right? So at most once is again, it's trivial. And at least once is also trivial when ABS enabled, right? Because ABS requires some replay processing. And then finally, if we want to achieve exactly once delivery semantics, then we need to have some transactional protocol such as two-phase commit, right? So this is a classic transactional protocol. We will not really dive into the details of this protocol. What we try to say here is that this protocol essentially tries to guarantee that the internal states and external states of some downstream system have to be committed at the same time, right? So the observation is that ABS, the asynchronous barrier snapshotting algorithm, can only have the effect on internal states. So we can see that so for stream processing, like one difference from batch processing is that we introduced the event time, right? Because we have to care about the event, the time when the event is generated. We can do correct analytics, and in order to have some window semantics, we have to introduce watermark, right? So this is also a side effect. We introduce event time to our system. One of the problem is that in batch processing, we can write SQL as usual. But for stream processing, SQL is not really time aware. So people keep adding a lot of time specialized keywords in various way to the SQL language. So for people to write streaming application in almost the same way. Right? So we can see that people add watermark semantics like for one single query, and they also try to watermark like for a table, let's say for a source. And people also try to add it at the level of one window function, right? So there's no really like the only correct way to do this. People just kind of learn about their customers' demands and then try to design accordingly. And the second thing is that I think after all these years, people have already figured out how we can really do stream processing in the correct way, like exactly once processing and the delivery, right? And for some cases, we can have some relaxed requirement. We can do at least once delivery whenever we have a primary key we want to sync to the downstream, right? So for example, let's say the downstream application of this stream job is a MySQL database. So we can specify a primary key in the table of that database so that when we produce duplicated results to the database can automatically discard the duplicated one. So this is like the current situation. So let's see some of the use cases. So for example, in this case, we are trying to analyze Twitter. So this query is basically asking how many times each hashtag is mentioned every single day, right? So what we can see from the example is that, first of all, within this with tag as query, what we do is that we try to select from the Twitter stream, right? And then we try to get all the hashtag out. And then we also take out the created time of each tweet. And then for the second select query below, we are basically doing a tumbling window operation here, right? So we are using the created timestamp of this text string to group by them, right? So we do the group by the hashtag and also by the start time of the window, right? So in this way, we can, count the times, how many times each hashtag is mentioned for each day, right? The use case is that we can calculate the click-through rate, right? So this is a very classic example in advertisement, right? So the calculation is done by, we have the number of clicks, and then we divide it by the number of impression. Basically, impression is how many times we showed the advertisement to the users, right? So basically, in this query, first of all, we are trying to count the impression, right? And then we also count the clicks, right? And for each ad, we join them on the advertisement ID, right? And then finally, we do this division at the outermost select statement. And the third example is about fraud detection, right? So we want to output an alert for any count that makes a small transaction immediately followed by a large one, where a smaller transaction is anything less than $1, and a larger one is more than $500, right? So this is Meetup examples. So here we can see we have some very special function called the lead, meaning that we want to, for example, for the first lead function, we are order the whole user transaction stream by the order of transaction timestamp, right? And we also try to partition according to the account ID, meaning that we only do the order by within each stream of the same account ID, right? And then we take like the second element out of it as the next amount, and we take the second element of the second lead function as the transaction timestamp, right? So basically, we are trying to get two consecutive transaction made by a particular account, right? And then we specify some condition in the where clause to filter out the events we are really looking for. So here we discuss some of the future usage, right? So stream processing, as you can see in the previous example, and the semantics we talked about when we introduced the event time, right? So typically people would use some window as the part of the query because people want to constrain the size of the state. And normally people only care about the most recent window happening in this streaming query, right? But nowadays, people can also do streaming processing for other type of workload, which is called incremental view maintenance, right? So we all know that if we want to do some OLAP, like online analytics processing, traditionally, we would just query that table again and again, even let's say we have the same query, right? So we just query the table, and then if there are some new inputs gets inserted into the table, we would still like rescan the whole table together with the new inputs to derive the latest insights, right? But right now, people can use like to maintain this kind of the query result set incrementally, right? The way it does it is try to take the source input of different kinds, right? So originally we have only like inserts, or we consider as appends. But right now we can take like inserts, updates, and deletes. Typically, it will be come from some OLTP database, right? So the good thing about using a streaming processing engine to do this is that we can maintain this view incrementally. We only incur the cost which is proportional to the changes we really need to make, right? So unlike the OLAP engine, we have to rescan all the data again and again. So one concrete example here is that we have a very typical query from TBCH benchmark. Right, so we can see this is a fairly complicated query that involve many joins. Right? So if we use a traditional OLAP system to do this, right? So we have to always rescan like these four tables, which are called customer, orders, line item, and nation. Right. So and we also need to do like four-way joins, which is really complicated and time-consuming. Right? So if we can incrementally maintain this materialized view, by a stream processing engine, right? So we can always get the freshest view of this TPC HQ10 as the updates come into the system, right? We don't need to rescan it over and over again. So you simply become more efficient, and not only in terms of the performance and also in terms of the cost. Right? So another challenge for stream processing is that nowadays we have a lot of cloud resources to utilize. So all these streaming engines that we have mentioned in this talk, they are basically designed for, let's say, before this cloud computing era, right? They just use local disk, local memory to store everything and do the calculation. But right now, cloud offers really a lot of different type of resources. So it really allows us to design a cost-effective architecture to utilize, different tier of resources. And one of the most important architecture is to do compute storage decouple, right? So by decoupling the compute and storage, we can scale the compute and storage independently. For example, if let's say the job is really compute intensive, then we just buy more CPUs, buy more advanced CPUs. If let's say we have to run a streaming job whose state is really large, then we just scale the storage, right? We buy more SSD or memory to make the processing more efficient. Right? So, and also like the cloud would charge different resources like with different pricing model, right? So normally we just using a local disk, and all the bandwidths are ours. We just try to utilize as much as possible. But for cloud storage, it is possible that the cloud vendor charges you by how many times you request for a remote, let's say, objects stored on the cloud, right? So we have also keep this in mind when we design a cost-effective architecture. The good thing is that if we can really to do so, a tiered compute and storage architecture can really enable a wide range of cost performance trade-offs, right? Because the user may not really care about really low latency for all kinds of applications. Right? So if they are the requirement is more relaxed, they can just use like cheaper resources to have more cost-effective way of processing. Yeah. So another challenge is that we need better elasticity to cope with fluctuation of streaming workload. Right. So typically, when we have some streaming processing scenario, like in e-commerce or let's say in streaming, the streaming type of YouTube streaming, let's say. So the typical characteristic is that the peak throughput is orders of magnitude higher than the throughput at normal times. Right? So the traditional approach is that to provision the resources for the peak throughput, which of course results in very low utilization. Right? So later people figure out how to do this scale in and out stuff. So they just try to stop all the compute nodes and do the scaling and scale out, and then they resume, right? The reason we need to spend some time during this stop the world and scaling scale out is because they use, for example, local disk to store their state, right? So the state are already partitioned on, let's say, a number of local disks. But the problem is that when we scale out, we have more disks, more compute nodes. We have to really repartition the state to the new ones. Right? So this kind of a repartitioning process is really time consuming. Right? And typically when we want to scale out is that when we have a sudden load spike. Right? So here, if we need to stop the world to do the scale out, it does not really make much sense because we just introduce some extra really high latency in this stage. Right? So this is also something we have to figure out in the future. Of course, and we also want to do like better resource estimation, and so that we can allocate the resource in more a finer granularity, so we reduce the waste. And the final one is that we just mentioned that we want to make this scaling process much more efficient. And finally, one angle is that we really want to build the stream processing system like a database instead of a standalone system. So as people use more and more stateful jobs in stream processing system, so we have to really manage the storage by ourselves. There are a couple of advantages. For example, if we really have a lot of queries, we can share the state, share the indices, share the data among different queries, right? So we simply just don't store the same state repetitively for a number of queries. And the second, because all these streaming queries are long-running queries, right? So we have the opportunity to optimize them as a whole instead of just optimize single by single, right? So the benefit of it is that we can create some common subqueries, and these common subqueries output some intermediate results which can be shared by the downstream of different stream queries. Right? So this is kind of a typical optimization that we would see in database communities. And also finally is that if we think about it, some popular database system, they would really emphasize on their storage engine instead of using some general purpose storage system, right? So I think for the system that we have talked about in this talk, they all just grab some off the shelf KV storage system, and then they just put their state inside that system. The problem is that we are really designing the system for streaming workload instead of general purpose workload. So we probably want to design our execution engine and the storage engine together instead of just leaving a lot of performance on the table. Right. Okay, so that's it. That's the end of the talk. Any questions?
The metadata how do you store metadata in your shared storage?
So the question is that how do we store the metadata in shared storage? So what kind of metadata you're talking about?
Create table circle, like table structure.
Okay, so we can store this kind of information in a separated service, like a highly available. Probably you can store in that because it's highly available, it's critical. So we can also just store in some etcd, some local KB storage system. Mm-hmm. So it's like the metadata is stored in one service, and the state managed by the stream processing is stored in some other different storage system. Mm-hmm. Okay, so the question is that do we have workloads that involve OLTP and stream processing, right? Sorry? Okay, so I think the common workload is like the OLTP and the stream processing are not really like in the same job. So OLTP is OLTP. For example, we have let's say a database which store all the information about users' purchase, right? So this is a typical OLTP example. Right? So when the OLTP made some changes, like transaction made some changes to the database, normally the database would have a bin log, right? So it basically logs out all the changes it made to the table, right? So we can use this kind of a change log in stream processing, right, to maintain a certain kind of analytical views you want to have, right?
Distributed logs, you also want to maintain in the etcd or other similar system. because if you are a lot of computer now, and maybe you can just allow one or two insert one table, so you will maintain a distributed logs.
Typically, people would just use Kafka or Posa to maintain these kind of logs. So,
Streaming data is future that you mentioned. Many of them you already incorporated in the protocol.
No, I think right now there are really a lot of stream processing companies out there, and a lot of them just reuse the Apache Flink and they just wrap them up as a service, right? But the problem is that all of these things, like mentioned in the future slides, I don't think Apache Flink has fully figured that out. So I think, this kind of a thing is like not a very clean research problem. It's really kind of a very dirty engineering problem, right? So about the scaling up, scaling out thing. Yeah. So I think it requires a lot of engineering effort to really make it right, make it work.
I wish more of the database that you
mentioned. Sorry?
Streaming database that you mentioned. So, is there any product that
Oh, you mean streaming database, right?
Yeah.
So, I mean, the typical example is, Writing Wave, which we are currently working on. And another streaming database is Materialize. Yeah. KSQLDB, I think the problem with KSQLDB is that it has some problem with its consistency models, right? So, because, like just I mentioned before, like we can accept inputs from some OLTP database, right? So each a set of change logs, for example, one transaction made some changes, and these changes all belong to the same transaction, right? So we want to either reflect all of the changes in the streaming job, or we don't reflect them at all, right? With KSQLDB, I think it cannot really make sure that like inherits the consistency level from the OLTP database.
You want the database streaming data?
Yes.
What is the currently the streaming database the storage engine you are using?
Currently, we design our own storage engine.
Our own storage
engine? Yes.
So you also make the transaction in the storage engine?
No, we don't really make transactional storage engine. Yeah, so we don't really need the transaction semantics like in RocksDB or LevelDB, because the thing is that when we process a job, the input event and the state are partitioned, right? So basically, it means that for a particular key, there's always only one writer write the value of that key. Right? So there's no data races, right? So that's why we don't really need transactional semantics.
So what is the data structure you use to store data? You are facing streaming insert, so there will be a lot of small I/O.
Yeah. So yes, because of that, so we use LSM tree.
But the LSM tree will handle that batch. As you mentioned, you can streaming database.
Yeah.
So for example, in the real use cases, some batches are really slow. For example, maybe the every 1 second it will only come to maybe one row's data or 2 rows data, and this will generate a lot of small data parts. And LSM tree is not good at handling this kind of use case because it will merge this small part in a background task. So how to handle this kind of task?
We can like group these events in memory before we. Yes.
And when you make this buffer, the user can query this data.
Yes.
It creates buffer.
Basically, what we want to make sure is that the partition of basically, the writer responsible for that key can query that data.
Okay.
But for other writers or readers, we don't care about that.
So the buffer is in the computer node. So the data in the buffer cannot be read from other computer nodes.
Yes, and it's not necessary, right, to be read from other computer nodes because it's already partitioned. Please go ahead. The question from Zoom.
Okay, can you hear me?
Yes, yes, yes.
Okay, so first of all, thanks for sharing. So the question is that, as we all know, the watermark is a tool to actually to make the data not correct. So in the industry, so we have two round batch jobs. One in some time to get accurate results. So my question is, what do you think of how the streaming database to achieve to get the correct results? Because as you know, we might have the device received orderly. So what do you think of this question?
So could you repeat like your definition of correct?
So in generally, we want one streaming database to serve all the requests, such as we generate a table every hour or every half hour or every day. So, however, due to the existing watermark, we cannot ensure every event received in the time. So we have to use watermark to check some later events. So
Yes.
this results in a problem that we might have to run the bad jobs to get the correct results to generate a table. Yeah. So I'm not sure whether the streaming database you are developing to solve this problem or have to solve this problem with some data lakes such as Iceberg or Hoodie. Yeah. So this is a question. I'm not sure whether my
I see.
expression is no.
Okay, so the question is that, you know, like we may set a inappropriate watermark, so that excludes a lot of late events. So eventually we have to do some processing to get like real correct view of the code. So, but what I would say is that if, let's say, you do some batch processing for the correct results, then at that time you are pretty sure that you have already have all the like input in your storage, right? Because otherwise you still get a incorrect view of the result. So I think one thing is that you can just kind of like abandon like watermark. You just don't set any watermark, so you can kind of keep processing the late events, right? And if, let's say, for a very long time, like maybe 1 month later, you are very sure that you will not have any late events afterwards. So you can kind of just ask the storage system to delete like the state which belongs to this time window. Do I answer your question?
Yeah, I think you are from a business view of this problem. So I think that's one. Okay, I think this is fine. Fine answer for this question. Yeah. I just think we'll, such as Reading with, will co-work with other data lakes to achieve this, or just achieve this within one system.
Oh, I see. Like, do we support some sync to Lakehouse, like Iceberg Hoodie? We currently don't support me, but we are definitely planning to support it. And I think this is really a classic workload for streaming, right? It's basically ETL, try to ingest the streaming input after transformation into a lakehouse. Yeah.
I see. Okay. Thanks for
So I think
answering.
it also depends on whether like the format the lakehouse support, you know, updates or delete retracts or not, right? Because some of the lakehouse only support like upserts. Any more question? Okay, maybe some offline question from offline audience.
As you mentioned, one computer node just related to one partition.
Mhm.
If you want to add more computer nodes, so you have to rebalance it, rebalance the data in the buffer.
So if we want to balance it, we definitely would, flush the buffer onto some durable storage first.
You already achieved the rebalance work.
I think, like our tech architecture has already kind of enabled this scale out or rebalance thing.
Okay.
But performance-wise, we have not benchmarked it.
Yeah, you didn't implement it, but the architecture can support this.
I think we can do this right now.
Okay.
So it is not really. I think the beauty of our architecture is that we do not really need to implement a very specialized process for this rebalancing, right? Because all the state is already in the shared storage. So after you scale out, you have more machines in the cluster. They just automatically so they first try to see whether the state they are looking for in the memory. If there's a cache miss, they just check the shared storage and do the fetch.
Because all the data is shared storage. It's just the cache again.
Yes.
Okay. But how you have a cache miss or mechanism?
And the one part, the partition you don't have replica, right?
We don't have replicas.
So if one node is down and you have to partition the data to other nodes, but how can you check the node is down?
Typically use heartbeat.
Timeout.
Yeah, basically timeout heartbeat.
So maybe I assume that the timeout is 10 seconds. So in the 10 seconds, the insert will stop.
Maybe, yeah.
I will consider about hot node issue. For example, because each node they have its own cache, and the cache data is different between each node. And some query maybe always dispatch to this one node server, and this server will be very easy, and system load will increase dramatically, and then the query performance will decrease. So how can handle this kind of scenario?
I mean, currently we haven't implemented a lot of optimization for the batch serving query, I suppose, right? So, I mean, obviously the simplest strategy is to just try to buy more memory.
Okay.
Right?
Okay. Inject more memory and cache more data. Okay.
So, any more questions from online audience? Okay, then maybe we just stop here and see you next time, maybe next month.